I can hear you.
Excellent, thank you. I would like to request from you guys that we record this session. If I'm allowed to record it, you can get a link and you can watch it all over again whenever you feel like it. Would that be okay for you? Anybody who protests, please speak up now.
I think I will need the recording because I'm kind of visually impaired.
Okay, that's very good. So that's going to be an
I have
extra.
a disability.
Yeah, that's going to be an extra help for you then, so that you can review it all over again. So I'll take it then that the recording this session is authorized by class. Okay, and for your information, I sent you a copy of the presentation just before the weekend. I have modified it slightly. It means that a few things have been added, a couple of slides, and a few slides have changed position, just reshuffling the order of them. Nothing really big whatsoever. So that we agree upon that immediately. Anything that you want to ask me, just stop me at any point and ask. So and if I don't see your hand up on the presentation, please just make a sound and I will stop to hear your question. Okay. To present myself, my name is Björn Brekkan. My main occupation right now is a well intervention supervisor with Equinor, the state oil company of Norway. I am an associate professor with NTNU. Right now, my engagement is in your class, Advanced Casing Design. And we will have, 6 sessions covering specific topics of advanced casing design. We'll take it a little bit slow today, and you will have a very special lecture. Today we are going to cover, first of all, an introduction and overview, and then later on the topic that we are going to cover is material science, the basic of making and what happens when you load steel components. And for our case, we will go specifically into what it means to a piece of casing or any other tubular, what it means when it gets stressed and stressed beyond its capacity, and why do we set the capacities like what we're doing, and so on and so forth. So material science is a very special topic. I have not seen that in any casing design class, and I feel that it has been missing. So that's why I'm going to give this to you, so that you know what it actually means. What does it mean when we are setting these limits, and what happens, and why are they important, and why are they sometimes in some contexts not important? All right, I will start presenting, and feel free at any point in time to stop me as said. So, can you now see my screen, the presentation? Very good. Yes. Very good.
Yes, we can see your screen.
All right. So I'm saying that this is lecture 1, And in the recordings, it will say part 1 of lecture 1, because we have a double hour, meaning hour 1 of session or lecture 1 and then 2. So I don't know if you guys saw, but at the end of the presentation is a link to a... Sorry? Go ahead.
Sorry, please, is it possible to
Yes.
zoom it a
Course,
bit?
thank you for asking. This is how big I can make it, or it will go outside of the screen. Can you see this? Yeah.
You can proceed.
You can also see the
I will
recording
try.
after. So this is how big I can make it in the screen here. All right. Yes. There is a link at the end of this presentation, and that link goes to a YouTube channel where all the presentations held last year, they are to be found in the same manner as what I just described, that there's like part 1 and 2 of every lecture. The only thing that is missing from that collection of presentations is the one that we're about to get now. That recording was not successful last year. So this presentation that you're having today, this lecture, is kind of unique in that sense. The reason why I am saying 1 out of 5 lectures is that I'm trying to hold one lecture that is for exercises. And that would be exercises apart from the normal hand calculations that you guys are having. You have a separate exercise with hand calculations that are very, call it exam oriented. And what I'm trying to give you on the sixth lecture is actually more leaning towards what we do in the industry, the software that we're using and how to use it, what it means, how some of these oddities are, how to interpret results, how to set it up, so on and so forth. Just to give a quick and brief introduction to the software, how it works. This slide is a picture from when we used to have a course in the autumn for the 5th graders. It used to be how to plan and develop a well. We were having the full landmark suite on every single computer that you're seeing in the picture, and we divided the class into groups, and you got an assignment like what it would be in real life, what is called a recommendation to drill, or some call it a statement of requirements that will be coming from the subsurface teams with certain call it boundaries, like an envelope saying that these are the targets we want to drill through, and we want to use this area to drill from, like a well slot or something. And then you would get a whole stability plot, and you would get a few other inputs that are subsurface related, and then everything else you need to plan. And that's what we did. And that might be an option this autumn too. It remains to be seen what would be possible. I know that for a fact these computers have been moved down to the rooms now called Oljen and Gassen. And you can, for yourself at any point in time, if you have access to those rooms. Otherwise, you will be given it if you ask for it. You can work on landmark, making well paths, making drilling designs, torque and drag, casing wear. You can make tubing design and casing design. Yeah, so that's one side of the exercises, and hopefully I can show this software briefly to you guys through this 6th lecture. I think that's quite valuable for you guys. And the regular exercise will be hand calculations that are basically targeting the exam and how you would go about to solve your exam assignment when that time comes. All right, and it says here that we have a draft compendium. I am very sorry that I never got to finish that. It's been at this stage, say 80–90% finished for some time now. I don't have the time, and NTNU doesn't have the resources either to finalize it, but it's more than good enough for this class. The reason why it's in draft condition is basically that I want to give you guys like a full set that you can use not only in this class, but bring with you when you start working as a drilling engineer, and to look up special cases in there to bring with you. I don't know if you guys did the autumn class called the TPG4215 Advanced Drilling 2. That compendium was also heavily made by me, but with also a lot of other good contributions in some areas from others. You may feel that compendium is very, very large, and it was made for the same reason. Bring it with you and look up specific topics. I know that a few people, they have given feedback and saying, previous students saying that they like this compendium for that reason. And as a student, of course, you hate it because it's so big, and you think that, of course, it's going to be very difficult for your exam. That's not at all why it was made in the sense that it is. And I hope that you can see that with the draft compendium here too, that it is for your benefit and not big and very difficult to get an overview of it. Just pick whatever you feel like inside. Any questions? Yeah, go ahead.
Sorry, I'm an active student, so yes. I'm just joining this semester.
That's okay. It depends on your background a little bit. What I'm doing here in this class is to give a quick and brief introduction to casing design also, so you kind of get the fundamentals so that you can jump into this topic, and it means that in a way you don't need to depend heavily on the previous classes. It would be good for you, of course, to have some basics in drilling design and so on. That would help you, but I'm kind of seeing that every now and again there will be students coming with a different background, so that's why I'm going to give you a speed introduction to whatever you need in order to comprehend and absorb the topics that we're presenting here. And if you feel that there are things you don't understand, or you're kind of finding it difficult to put them in the context, I would definitely be open for questions. you can either email me, and the best email would be the Gmail that I gave to you guys, bjorbre@gmail.com. That's the one that I'm most easily available on. My NTNU email, that one is a little bit on and off, and I'm having a little bit of difficulties with my account. So, but just contact me and definitely ask in class, no problem whatsoever. With these things being said, I'm just going to jump to it, and the first slide of the class relevant for material design and casing design. Basically the question, what is casing design and why do we do it? It is the answer, what is the engineering process of designing the required size, grade and placement of casing strings. That's basically what it is about when all comes to everything. And asking the why, it is to stabilize and support well bores, preventing the well from collapsing, isolate different formations and creating integrity. Integrity, I hope that you all have a good understanding of integrity. It's one of the major tasks, basically going on from early planning of a well until the very end of the permanent plug and abandonment. What we do in casing design is to look into and simulate absolutely everything that we think may, with a low or even of course a high probability, is going to happen to our well. And then what we do is to simulate all of these cases. When we do the hand exercise later on, there is a specific situation that we are calculating. When we do the exercise using the software, we have to simulate all these specific cases. These specific cases have a specific name, and I will get back to that part. Why we are doing casing design is to ensure that we can control the well pressure. The casing needs to be stronger than any formation exposed. That's how we present it. Sorry, that's how we set it up. That's one of the regulations for doing casing design. And also the casing is set up to provide a pathway for fluids, and that's just in one context simulated for the drilling fluids, and in the other context later on for production or injection. That being said, cuttings re-injection is also a case, and gas lift. So it's not just fluids producing from the reservoir or injected into the reservoir. When it comes to integrity, there are many aspects to consider. This picture that has been put in the back, it is to show especially Norwegians used to having oil and gas industry being offshore. In many cases onshore, wells are being drilled through aquifers containing drinking water. It could pollute the formations that go a long way and into, say, a drinking water source later afar, or it could be formations that come up into the ground level, and things that are linked together, say formation containing salt water, and you connect it subsurface into something that goes up into the day. These things we need to prevent. And one of the things that may happen, of course, is an underground blowout. If you link two formations, one that is high pressure and one that is low integrity, low consolidation, or just plain weak, you may have a situation of an underground blowout. Integrity is a very big topic. So what, why, and here arrives the how. How we do it, we will of course detail that in this class. And eventually we will arrive at a good overview of how we do it. We will of course start with the theory, the basic theories, the calculations, because a software may sometimes give you an answer that you don't really understand or misunderstand. What is important is to have the basic understanding of casing design so that you know how to use the result from any software in the appropriate way. And of course, software is software, and it may sometimes actually give you the wrong answer. Yeah, so you need to be able to detect that. All right. Yeah, as it says here, the best overview is actually to do the theory, and then once in your hand calculation, the one thing that will be your assignment, that is going to be exam oriented, and it's one specific case, one situation in the life cycle of the well that you're calculating. We call this a load case. But when you're going to the software, you're simulating all these scenarios, all these so-called load cases. And that's going to give you what I think is the best overview of what casing design is. We will now start on the theory of material science. We're going to discuss steel and its properties. And we're going to go all into detail at the molecular level, atomic level. Many of you remember from early chemistry classes how atoms are being put together into molecules. Now, steel is a metal, and metals, they are set up in specific structures, not like single units in the same way like, for example, a water molecule would be. They are in a lattice, meaning they are kind of a long homogeneous systematic unit, whereas what we do in order to understand the system of this lattice is to set up what we call a unit cell. And for metals, the most common ones are the two ones that we are seeing in this picture, BCC and FCC. The FCC, I forgot now what the BCC stands for, but it's phase center cubic or something, the FCC, and that's very simple because you see the one on the right, it has 5 atoms in the plane closest to you, and that's the system of it. you can rotate that cube in any way, shape, or form, and it has these 5 steel atoms on the plane close to you, whereas the BCC, it has 4 and atoms in the plane, outer plane, and it has 1 atom in the center of the unit cell. The FCC doesn't have anything in the center. Excuse me. These 2 units are the building blocks of steel, and they present different properties. Steel would behave different if it is in the BCC structure of its lattice or FCC. Just to throw out one simple thing immediately, one of these has a fatigue pattern and the other one not so much. So, for example, the reason why aluminum is used comprehensively in the area in planes and air industry is that it doesn't really fatigue. It's the FCC structure, if my memory serves me right. It's not essential to this to casing design as per se, but it's good to know that there are different properties and different behavior. And the most common, of course, of all casings would be the carbon steel. We call it carbon steel because it has a certain amount of carbon in it. And carbon in steel, it is as presented in this yellow tiny atom inside the lattice of the steel. We often call this interstitial, meaning it goes inside the lattice and it kind of bends the connections, the bond between the steel atoms. And if your memory has failed you a little bit, the bond between the steel atoms is basically sharing electrons. Sharing the electrons that creates the special lattice and bond that is between the atom. I see a hand up. Please ask.
No, everything is okay. You were just trying to know the meaning of BCC the other time.
Thank you.
So I just wanted to say it, but everything is okay.
Yeah,
body center.
That's what it is. Thank you. So body center.
Body cube center.
Thank you. Yeah. Just for curiosity, have you been looking into material science before? Is this new to you, or is it old stuff?
I worked in the oil and gas industry before as a logistics officer or inventory analyst. So we usually go to the warehouse and we did a little bit of materials management.
And the way you're answering,
just a little bit of it. I was more into warehousing and inventory management, but I did a bit of
and the way you're
material
answering
management.
This is exactly the reason why I said that this is going to be an important topic in casing design, because typically teachings of casing design doesn't really include the basics of the material and to understand the background and the details of how you manufacture the pipe. and why you do it that way, and how it kind of influences the strength or reduces the strength or other properties. So yeah. All right, and back to the topic. Feel free at any time to just say whistle or interrupt me. As said, you see the carbon atom here sitting inside the lattice, and you can imagine that putting more carbon into the steel body, it will create more tension. You see in the center on the biggest of these lattices, that they call it a plane drawing on the left, that the bonds are kind of bent around the carbon atom, and more carbon means more bending, means more stress in the lattice, means more kind of brittle behavior. Yeah. Stronger, but also at the same time more brittle. And there are altogether 4 atoms that we call the 4 small ones that influence the steel lattice in this way. It's hydrogen, boron, carbon, and nitrogen. Yeah, they can form interstitial connections or setup of the steel lattice. Now, what we all need to know immediately, and probably you heard rumors, is that the hydrogen atom, you get free hydrogen or even hydrogen components like acids, they may have hydrogen atoms going into the steel. For some reason, they love to go, free hydrogen loves to go into the steel components and lattices, and that is kind of extremely critical. We can get back to that a little bit more in detail, talking about corrosion. That is a topic that I also introduce if there is time. Last year there was some talk about it. I'm not sure to what extent we talked about hydrogen last year, but to give you a brief insight, hydrogen kind of tears up and breaks the lattice. It creates crevices and cracks in the steel, blisters, hydrogen blisters. So it becomes like a biscuit, and it completely loses its strength. So hydrogen is extremely bad for steel. Free hydrogen ruins a steel structure when exposed to it. And the time frame is sometimes extremely short. It could be hours, it could be days, and with enough hydrogen, of course, available. Other connections that influence steel. We all have heard talk about stainless steels. Stainless steels, typically what we call stainless steel, it starts with an alloy of 13% chrome. It would be different things on the internet saying that it starts at maybe at 12, maybe at 11 in some places. It could be others, but in many cases in the oil industry we use 13% chrome. Then we say it's a stainless steel. Now we're going to talk more about the structures of steel and how they become stainless, or call it develop corrosion resistance when you add only 13% chrome. We can talk about that later. If I should forget, remind me, and I will get back to it. The reason why I want to wait is to give you a little bit more, call it structure to build on and understanding, and you will more easily see it. What we see here now would be substitutional alloys. Anything but the 4 small ones would typically go into the lattice. There are many types of atoms that easily forms and go into and substitute steel atoms, and chromium would definitely be one of them. Excuse me again. What we're seeing here is a load cell. I'm gonna zoom in a little bit. These ones are used in order to test the strength of steel. What we see here is basically a test specimen. It has a elongation meter attached to the body, and you see it's a load cell where you stretch the specimen, you elongate it by moving the lower block, the upper one being stationary. You're measuring the force and the elongation at the same time. It's a load cell. What we get out of this load cell is this stress strain curve. What we see in the bottom would be the load cells as the specimen as it's being strained in the load cell and how it affects the specimen. It's stressed and elongated until it fails, and the failure would look something like on the right. This curve is exaggerated a little bit, but it's very, very important for steel. We can see the derivative of the stress strain. It's where we get the Young's modulus, and for steel this is a specific number, and it will be the same all over. If a steel is stronger, it means that it follows this stapled line, whereas a weaker steel would follow the red line. And what we call is the yield point of steel is where it starts to deform. By definition, when a piece of steel has 0.2% permanent deformation, that's its yield point or yield strength. We have a complete linear region that's all up until the point A. You stress it until point A, like so, and then you relax the stress, and it will go back to its original shape. Yeah. And you will say that also about B, meaning that it doesn't have a linear part, but still it goes back to its original shape, and then you stretch it a little bit more and you get to the yield point C. When we stretch it beyond point C and we go to point D, we have what is called plastic yielding. Steel is the only metal that I know of that actually has this. There might be others, but I haven't really seen that in this specific, call it dip in the stress strain curve for any other metal. I might be wrong, but I've just not seen it. This dip, as it goes beyond point D, it starts building again. And that's when you get what we call strain hardening. And that's an interesting part, because the steel actually behaves as if it is stronger if you relax it from this part. Let me see if, yeah, we'll get back to that part. It's like you stress it and you relax it, and then the next point, you have to go to the same stress as when you relaxed it. You have to go to, say, for example, you stressed it to this point here. Then that's where you need to go to in order to have more deformation. So that's why we call it strain hardening, or in some contexts, and when we manufacture casing, as we will see later on, that's like when we do work hardening, producing and creating casing all up until the point where we get the properties like wall thickness or strength or whatever it is for casing. We often get into this area, and we need to look into how to deal with that after. We'll get into casing manufacturing after the break, which is kind of imminent now. Steel is homogeneous. It means that when you stress it, and yes, it's Hooke's law, like you see here, the Young's modulus. It's the stress over the strain. We saw the formula for strain in the previous slide. I can go quickly back to it so you can see it again. It's the stress creates a strain, which is the delta elongation divided on the complete length, original length. Extension due to load, as it's described here, at the original length. And that behavior also is the same in compression. That's how it is. We will quickly talk about, in the last 2 minutes before the break, how to create a steel, how steel is being made into the fundament of a piece of steel for casing. This is a furnace. A furnace is where you melt down the ore, the iron ore, typically hematite or magnetite, as it is listed here, and we typically add scrap metal. We add other things like limestone, coal or coke, what is called, fluxes for removing impurities that comes in there. It will be always some impurities coming out of the iron ore. And if we want the steel not to be like a standard carbon steel, we add the manganese, chromium, nickel, and others into the furnace. Maybe not so very visible here. The furnace, it has different temperatures. In the top, it will be typically around 200-300 degrees, 500 further down, and so on and so forth, until you get to something like 2000 degrees Celsius or 3600 and some degree Fahrenheit. In the bottom is a pure liquid steel melt, and that's where we take out what is going to become a piece of pipe, a casing. Out of the furnace up here comes liquid steel, and the liquid steel is then formed into what is called a billet. That is just a metal rod. We see the process of making a piece of pipe here on the right. And with that, I'm going to take a small break, and we'll continue looking into the steel properties, and we will get more into the details and investigate more how this process that you're seeing here of making casing, how that is being what takes place at the atomic and molecular level, if you can talk about molecular levels in a steel lattice as per se. All right, any questions before we yeah, go ahead.
Okay. Yeah,
Yes.
I have a question regarding the mechanical behavior of steel.
Yes.
You were showing the graph of stress against steel. I remember there's something called ultimate tensile strength.
Yes, but
Is ultimate tensile strength the
I'd
same thing
say
as
that the
the
ultimate
the
strength
steel
would be
hardening?
here at the failure, and the yield strength is here. I can give you a quick answer that probably is going to solve this question for you now. When it comes to deforming steel, that is what is taking place on the curve here. We need to have drift through our pipes. We need to be able to run a plug or a bit or something through the casing. If we deform it, we don't exactly know if we will have the drift. That's why very often we set the limit in casing design to be below yield. In some cases, we can accept going above yield. Those will be very, very few and specific cases, and you need to have the full understanding of what you're doing. Yeah, but when it comes to ultimate yield strength, there are calculation techniques going to calculate back to the yield strength. That is in burst calculations. But yeah, we'll get back to that later on in class. All right, remember to ask me if you want more about this later on. Okay, see you guys in a few minutes.
Okay.